Hello, welcome. My name is Aymeric. I am doing my PhD in mathematics in Oxford, and I'm also working in artificial life in Cross Labs, Japan. And here I am presenting you my research titled Population Network Structure Impacts Genetic Algorithm Optimization Performance, in which I am looking at what happens when we change the structure of the population inside the genetic algorithm, instead of having the standard complete one that we all know. The standard GA assumes implicitly the existence of a complete network. It does so by assuming that all individuals can mate with each other through crossover during search, based only on the fitness criterion. However, these sort of complete networks are actually quite rare in nature and societies. So this leads to wondering what happens if we have other structures and what is the impact of these structures on the GA performance for instance, optimization tasks. In the plot here, I am showing a few examples of various network structures from Erdos-Renyi on the three top and Albert-Barabasi in the bottom algorithms with 10 nodes. And you can notice that the complete network, which is the standard GA one, is only this one. So this one assumes a high number of links and every node is connected to every other node. But many others are possible. And the whole point of this work is to identify what happens to the GA performance if instead of having a complete network, we have something somewhat disconnected, something completely disconnected, or some other complex structure, such as the tree network or the star network. The network genetic algorithm is a variation of the standard genetic algorithm that implements this network aspect of the population. It uses very standard operators. So we start with random initialization in the search space. We have fitness proportionate selection. We have the standard crossover. We have Gaussian mutation. So far, everything is very standard. What we modify with the network genetic algorithm, NGA, is the selection operator. In the standard GA, consider this, you select two individuals based on fitness, and this selection is independent, and you have these two individuals, and you're very happy with it. If you introduce the idea of networks into the selection method, you will essentially constrain mating in this population. To give you an example, let's assume that we are in this network, so the Albert-Barabasi network with a preferential attachment parameter m of 1. We just adjust the number, the strength of the preferential attachment mechanism. And if we have selected this first central individual as by fitness as our first parent, then the second individual to be selected will not be any node in the network. It will be one node based on fitness inside the direct neighbors of this first individual. So here the neighbors of this central node are this one, this one, this one, and this one. So we are essentially doing a first unrestricted fitness-based selection for the first parent. And in the second, we are doing a fitness proportionate selection inside the neighborhood of the first agent that was selected. So we are doing this fitness proportionate selection in all the direct neighbors of this first agent. And basically, after that, we are going to study how different parameters for our network algorithms will impact the performance of the GA, of the NGA, when we have these modified selection operators. A few words on the networks themselves. So the Erdos-Renyi and Albert-Barabasi, respectively ER and AB, are very standard network structures in network science, and they each have a sort of parameter that governs their structure. In the Erdos-Renyi random network, the parameter named P is the probability of attachment between any two nodes. So any link between any pair of nodes has a probability P of existing. So when P equals 0, you have no links at all. And when you have P equal 1, all the links are present. So this is the complete network. And for intermediate values of P, well, you just have an intermediate number of connections. In the Albert-Barabasi network, the main mechanism at play is preferential attachment, the idea that well-connected nodes are more likely to attract new incoming nodes, just like the the internet, for instance. So the parameter M is just the strength of this attraction. So when it is rather low, the network seems quite balanced. There is no real hub that is forming. When it's intermediate, you start having some hubs that appear. For instance, this one and this one are fairly central already in the network. And when M is increased up to almost the population size here, 10 minus 2, this is the maximal value it can take. We have a star network in which a central hub is essentially connected to everything else. To illustrate this impact of network structure, we'll be using 3 test functions with a dimension of 2. So we've chosen the radiating function, sphere function, Ackley function to have different sorts of levels of complexity, of levels of roughness, of levels of local optima. And we wanted just to have at least 3 different functions to be sure that we're capturing some general conclusions about the behavior of the network genetic algorithm. We are only considering a dimension of 2, and extending this to higher dimension is a very good idea for further work. But here we'd just be concerned about running these NGAs with different network structures on these test functions to try to optimize them, using baseline parameters to try to identify the impact of the parameters P and M in the 2 network types. Here I am just showing the GA parameter configuration. This is not fine-tuned. This is purely this very standard, very baseline configuration you can imagine from the different works that are very ancient now, but we are still taking this as a reference point. And during the runs, we won't be changing the population size or the crossover mutation rate. We'll be only varying the structure of the networks. So this was just to show for reproducibility and for transparency what the setup of the GA was. You will notice that the number of iterations and all generations is rather low. It's 100. And the reason is that when we run the GA, most of the interesting stuff seems to happen up to the iteration or generation 100. These plots show you the average fitness of the different GAs. So the ER network with P equals 0, 0.5, 1, the AB network with N equals 1, 25, 49. So using a population size of 50, as shown before. The blue line indicates you the average fitness for the Ackley function. The purple one is for the radiating function, and the red one is for the sphere function. And this plot just shows you the behavior of the GA, the average across 10 repetitions, just to show you what happens with the number of generations first. And we can already see that the sphere function is fairly easy to optimize. Obviously, it's very convex, it's very nice. The programs have a harder time with the Ackley function, notably. But just what this outlines is first that we can restrict our analysis to the first 100 periods, and this is already interesting and sufficient. And second, that some clear differences seems already to be emerging from changing network structure. The big example is, for instance, comparing this star network that doesn't seem very nice. You know, it doesn't seem to have a lot of potential in optimization compared to other structures. And even here, as we increase density, it looks like these 2 extreme levels are not performing as good as this intermediate level of connectivity. So this motivates to study in a bit more depth what happens with respect to the probability of links in ER networks first. Here, the plots still show the average fitness for the different functions, but this time, instead of conditioning on time, we condition on the network probability, so the P parameter. What we see here is that the average fitness for the test function optimization average across 10 runs for each value of P basically gives a lot of emphasis on connectivity. And one important property of these ER networks is that at some point, there is a phase transition in which the network becomes connected. And for our value of population at 50, this threshold is around 0.05. And you can really see that these networks, when they are disconnected, so in the very left side of the plots, the performance is the worst. So the average fitness is very high because we're trying to minimize the functions. But as we get connectedness inside the network, that is when there exists a path that goes through links between any pair of nodes, suddenly performance really increases. The more puzzling finding is when you observe these polynomial fits of order 4, it looks like these extremely high levels of connectivity. So when we get close to a very complete network, so a p close to 1, basically performance doesn't seem to increase much. And in fact, it even suggests that the performance might be decreasing, like the fitness increasing. And it looks from graphical analysis that there will be intermediate optimal levels performance for intermediate values of P of connectivity. To me, I can interpret this finding as being that highest densities may not be optimal for especially the Ackley function, the Rastridin function, because of the number of local optima. So essentially, if your network is too well connected, it's much easier to have premature convergence or to just fall into a local optima. While if you have a sort of degree of disconnectivity in the network, if you have some more independence, and if the transmission through crossover is a bit slowed down, it may allow you to give you more time and flexibility to find these global minima among all these different local optimum. Replicating the same analysis for the scale-free Abel-Barabazi networks, here the results are much clearer, and we can basically see that there is an optimal recursive attachment strength. If you have something that is too low, that is if you don't have any hubs really in the network, fitness is rather high, so we're not really very happy. And if the network becomes extremely centralized, the fitness is extremely high as well. So we are definitely not happy with these structures. And it just gives a general insight into what network structures are resilient, are optimal for performance. And here it clearly shows that low centralization, low distance networks work best. That is, networks that have not so much centralization, not too much isolation. They can have a few hubs, but what's very important is that they are sort of distributed. And I cannot help but think about biological networks when I'm seeing these results. There is clearly a connection between what seems to be the optimal network in terms of GA optimization and the networks that we know in biology that have evolved in other ways for efficiency as well. What's important about these intermediate size network in terms of proportional attachment strength M is that they exhibit what in network science is called low average shortest path length. The shortest path length, the average shortest path length is the average of all the shortest path between any pairs of nodes in a network. So a very low average shortest path tells you that essentially it's very easy to travel from any node to any other node. So the network has some good connectivity inside. It's very easy to transmit information from one part to the other part of the network. And this low average shortest path length seems to be very favored by the GA because it allows good solutions to percolate through the network and be improved by other nodes. But when you have this low average shortest path length with extremely centralized systems, and this is the right part of these plots, the whole mechanism falls apart because you're really relying on possibly the mistakes of a central node, and this central node can really act as undermining the performance of the whole population. The last finding I would like to show you is that these network GAs outperform the standard complete GAs. And by that, I mean that if we plot the average fitness of the standard GA and the best fitness we achieved in all the different networks that we considered, if the standard GA with the complete network is never the winner. And in fact, there is a significant improvement of 53% in average in fitness, considering other networks. ES star and AB star designates basically the best network inside each category. So it doesn't tell what characteristic it was, it's just to show you that we actually, by focusing on only one structure, the complete network, which is the GA, if we just stay with this structure, we are missing very important gains in fitness, just from having different structures and intermediate levels of completeness of connectivity inside the network. And this effect is present for any times at which we look at, and is present for all the pretest functions. And this, to me, highlights a new opportunity for network tuning. Just like we are tuning our parameters for optimization, we can tune the network population structure as well to gain significant gains in fitness. Further work on this topic could include testing the robustness of these findings, so testing for other GA configurations, higher dimensions, other test functions. It gives a possible gate towards dynamic self-adaptive population networks, asking the question of what evolutionary mechanisms or heuristics could converge to this optimality. And finally, it helps at starting network tuning as part of our toolbox. I thank you for attending. All the codes, everything is in the GitHub below, and my contact email is there as well. Thank you, and see you at the conference.